Hi there. We looked last time at the Enigma machine, and what we'd like to do today is talk about some of the mathematics behind what the Enigma machine is doing. And so we're going to look at permutations a little more closely. A permutation is a one-to-one and onto function, also called a bijection, from a finite set to itself. In this case, we're permuting the 26 letters of the alphabet. Sometimes we'll refer to these by numbers instead of by letters. If we are talking about a permutation of a set of n objects, we sometimes call this S sub n. If we talk about the set of all permutations. So there are 26 factorial in S26. So S26 has 26 factorial permutations in it. That is a lot of permutations. So this is a very large set. It's for those of you who have had an abstract algebra course or a modern algebra course, it is a group under composition. And it's and so we can take advantage of some of its group properties. If you haven't had a modern algebra course, that's okay. We're going to talk about the specific group properties that we'll use as we go along. And that's all we'll need to know. All right. So how do we write a permutation of a set? There are two notations that are commonly used. One is called two-row notation, where we list the plain text and we list the ciphertext underneath it. If we are permuting 1, 2, 3, 4, 2, 4, 3, 1, 1 goes to 2, 2 goes to 4, 3 goes to itself, and then 4 goes back to 1. So that's, we're just listing input and output, so to speak. Now, because permutations are functions, we compose them in right to left order, and this is not anything new. This is if we write f of g of x, or if we write f composed with g of x, we always do functions right to left. Permutations are functions, and so we do them right to left. And so if we do sigma 1, sigma 2 in this order, that means we're writing them left to right. I mean, sigma 1, sigma 2, but we're going to do sigma 1, sigma 2 first. So 1 will go to 3, and then 3 goes back to 1. And so 1 goes to 1, then 2 goes to 1, and then 1 goes to 3. And so 2 goes to 3, and then 3 goes to 2, but then 2 stays the same in sigma 1. So 2 goes to itself, and so 3 ends up going to 2. That's what happens if we compose sigma 1, sigma 2. If we compose them in the other order, sigma 2, sigma 1, 1 goes to 3, but then 3 goes to 2. So 1 went to 3 and then on to 2. 2 stays the same, but then goes back to 1. And then 3 goes to 1, but then comes back to 3. And so 1 goes to 2, 2 goes to 1, and then 3 goes to itself. And so that's what we get when we do sigma 2, sigma 1. And so one of the things we immediately notice, immediate conclusion, the order of permutations matter. Permutations are not commutative. So that's what we get from this exercise here is a demonstration that permutations are not commutative. Okay. Two-row notation is easy to read because we're just listing input and output elements. It's sometimes hard to typeset because you have to go in and set up, an array with multiple rows, especially if you're not comfortable typesetting in LaTeX. But even in LaTeX, it takes a little bit of work. And so we also have a one-row notation, where in one-row notation, we have sort of a list of things, and if the first element, if the first element is being a plain text, we follow it by its corresponding ciphertext. But then we interpret the second element as a plain text, and when we follow it by its ciphertext, and then so on and so forth, until we see a repeated letter, in which case we get to a plain text that wraps around back to the original term to be the ciphertext. So in other words, whatever this permutation does, it takes the a sub ith term and sends it to the a sub ith plus 1, with the a sub kth term going back to a sub 1. And if x is not in that set, then it sends a letter to itself. So a cycle of length k is sometimes called a k cycle, and a 2 cycle is just called a transposition. It just takes 2 objects and switches them. So let's do an example of cycle notation here. We want to write this permutation using cycle notation. So we're going to start with a 1, and I see that 1 goes to 2. And then I see that 2 goes to 4, and then I see 4 goes back to 1, but I already have a 1 in my cycle, so I close the cycle. And then everything has been listed here except for a 3, but 3 goes to itself, and so it's just nothing happens to the 3. 3 cycles all the way back to itself. Okay? And in fact, it's optional to write a cycle of 1. So 1 cycles may be omitted. Anything higher than a 1 cycle has to be included, but 1 cycle may be omitted. So this is correct, or this is correct. Okay. So not all permutations turn out to be cycles. Some permutations turn out to be a combination of cycles. Okay. So number 2 says to compute this product. All right. So we're going to start with a 1. This function does nothing to 1. 1 goes to 1 because it only moves 3, 4, and 5 around. So 1 stays at 1 when we do this function. Again, we start on the right, but then this function takes 1 to 2. So 1 goes to 2. So then we look to see what happens to 2. This function still does nothing to 2, so 2 goes to 2. But then this function takes 2 and sends it to 4. All right, so now we see what happens to 4. Well, this function is now doing something. It takes 4 to 5, and then this function doesn't do anything with a 5. And so we have a 5 here. So let's see what happens to 5. This function sends 5 to 3, and then this function doesn't do anything with 3, and so 3 stays the same. And then let's look at what happens to 3. This function sends 3 to 4, and this function sends 4 back to 1, and so 3 ends up going back to 1, but 1 is at the beginning of the cycle, so I close this out. And so when I combine these 2 cycles, this is the cycle that I get. Okay? All right. Cycles are said to be disjoint. Here's a formal definition. If A of x doesn't equal x, in other words, alpha changes x to some other character, then beta doesn't change x to another character. Beta just says x to itself. And then vice versa, if beta of x moves to a different character, then alpha leaves x alone. So that's what it says it means to be disjoint. If either function moves a character, the other function leaves that character alone. But more simply, two cycles are disjoint if they have no numbers in common. That's the easier way to recognize it. This definition is overly confusing, but it's correct. And earlier we said that order matters because permutations are not commutative. We have a special theorem here. If we have disjoint cycles, they do commute. Okay? So this is a special exception. So permutations do not commute unless they are disjoint. Okay? So we can prove this. We're going to prove this by cases. The easy case is if alpha and beta, neither one of them do anything to x. So if the first case is that alpha of x is equal to x and beta of x is equal to x, well then alpha beta of x is just x and beta alpha of x is equal to x. So alpha of beta is equal to beta of alpha. That's the first case. That is if we have a character that is not part of either permutation, that is, both permutations leave that character alone, then it doesn't matter which order we leave them alone in, and we're leaving it alone. And so there's nothing to happen there. In the case where alpha of x doesn't equal x, then we know that beta of x does equal x. Okay? And so, because that's what it means to be disjoint, that's the definition. If one of the functions does something with x, then the other function has to leave it alone. So then, alpha of beta of x, since beta doesn't do anything to x, that's just equal to alpha of x. Now, this is a little trickier because we want to show that beta of alpha of x also equals alpha of x. But alpha of x is obviously part of the permutation alpha, since alpha of x is an element in the permutation of alpha. Beta of alpha of x has to be left alone by the definition. Anything that alpha touches, beta leaves alone. And so alpha of beta of x is equal to alpha of x, and beta of alpha of x also equals alpha of x. Then the third case is very similar to the second case. If beta of x doesn't equal x, then alpha of x does equal x. And then we can just say, without loss of generality, we're starting from the right side instead of from the left side. But I'll go ahead and write it out. Then beta of alpha of x is equal to, since beta of alpha of x is equal to x, is beta of x. And since beta of x is an element permuted by beta alpha of beta of x will also equal to beta of x. Alpha has to leave it alone. And so both of these turn out to be the same again. And so in all three cases, we get the same thing, whichever order we do this in. All right. Okay, so let's move on. Disjoint cycle decomposition. So if we have any permutation in Sn, we can break it up into disjoint cycles. So sigma is equal to a product of these disjoint cycles. The advantage of that is that the disjoint cycles commute. Sigma may not, but the individual disjoint cycles do. So the advantage, sigma breaks up into commuting elements. All right. So how are we going to write this as a product of disjoint cycles? So pick a starting element. We usually start with 1. Start with 1 and follow the cycle. To the end of a cycle. I'll show you what I mean by that. 1 goes to 4. So that takes care of the 1. And then 4 goes to 5. And then 5 goes back to 1, and that closes off a cycle. So then start with the smallest element that hasn't been seen yet. Start with the smallest unused element. And follow it to the end of a cycle. So this time it's going to be with a 2. 2 goes to 9. 9 goes to 3. 3 goes back to 2. All right. And we're just going to repeat step 2 until we're out of elements. Until we have no more elements. So at this point, the smallest unused element is a 6, and 6 goes to 7, and then 7 goes back to 6. And then the smallest unused element is an 8, and 8 goes back to itself. And so if we string all of these together, we get that sigma is equal to 145, 293, 6, 7, and again, an 8 is optional. Any one element cycle is optional. So you could write it either way, 145, 293, 6, 7. Okay? And that is sigma written as a combination of disjoint cycles. All right. Cycle reduction. So now that we have these cycles, this cycle has 3 elements, this cycle has 3 elements, this cycle has 2 elements. Every cycle can be broken down into transpositions. And remember that a transposition is a 2 cycle. Okay. So I want to write this 5 cycle as a product of transpositions. All right. So what's happening here, 1, 2, 5, 3, 4, is that I've got sort of these objects, 1, 2. I don't know why I'm drawing them this way, but that's okay. And number 1 is moving to position 2. And then number 2 is moving to position 5. And then number 5 is moving to position 3. And then number 3 is moving to position 4. And then finally 4 is moving back to position 1. And so 1 goes here, 2 goes here, 2 goes here, 3 goes here, 4 goes over here, 5 goes right there. Okay? So here's what we're going to do as a way of putting this into transpositions. We're going to pick some element, and we usually just pick the first element. And we want to get the first element into the correct place. But we can only do it with a transposition. Well, that means we want to transpose 1 with 2. So what we're going to do is we're going to start, put 1 in the correct place. So we switch 1 with 2. So what we have now is we had 1, 2, 3, 4, 5. We want 4, 1, 5, 3, 2. That's what we want. But I've just switched 1 and 2. And 1 is now in the correct place. All right, now this is a little tricky. We want to put 2 in the correct place. But remember, 2 is currently occupying position 1. But 2 is temporary in position 1. We want to move the thing that's in position 1 over to here. And so we're going to swap positions 1 with position 5. And so that's going to get me a 5 up here and a 1, 3, 4, and then a 2. Okay. All right. Well, what we could do is then go ahead and put 3 in the correct place, but I want to show you a different pattern. When we moved 1, 2 got moved as well. When we moved 2, 5 got moved as well. What I'm going to do now is go ahead and move 5 into the correct place. Put 5 in the correct place. But 5 is temporarily in position 1. So I want the 5 to end up here, so I need to move the 5 to position 3. So the thing in position 1 will switch place with the thing in position 3. And so now we have 3, 1, 5, 4, 2. All right. And then the next thing we have to do is take the 3 that's in position 1 and move it to its correct place. Put 3 in the correct place. Okay. There's a pattern here. Whatever is the second number of the cycle becomes the number that we move in the next step. All right. So to put 3 in the correct place, again, 3 is temporarily in position 1. I want to take the thing that's in position 1 and move it to position 4. So I'm going to switch position 1 with position 4. Is what's going to do that. And then what happens is we now have 4, 1, 5, 3, 2, which is exactly what we wanted. And so we had to do 1, 2, 3, 4 different swaps. And we had to do them in this order. But remember that compositions are done right to left. And so 1, 2, 5, 3, 4 is equal to 1, 2 on the right, 1, 5, 1, 3, and 1, 4. Okay? And there's a pattern here. All of these start with 1, and the other other numbers are these numbers in reverse order: 4, 3, 5, 2, 4, 3, 5, 2. And so if you know the pattern, there's a fast way to take a cycle and turn it into transpositions. Okay? Theorem 2 says any permutation can be broken up into cycles. Theorem 3 says any cycle can be broken up into transpositions. And so when we combine these together, any permutation can be written in terms of transpositions. And we define permutations to be even or odd depending on the number of transpositions in its representation. This is going to be the basis for some parity arguments that we can do later on. And so, as an example, the permutation that we did in this example here broke down into 1, 2, 3, 4 transpositions. And so this is what we would call an even transformation, or an even permutation. Okay? All right, let's move on. So let's try writing this permutation here as a product of transpositions and determine whether it is even or odd. Okay? All right. So let's start by writing it as cycles. So first we're going to write it as cycles. So 1 goes to 4. 4 goes to 5, and then 5 goes back to 1. I think we've done this already. Then 2 goes to 9, and then 9 goes to 3, and then 3 goes back to 2, and then 6 goes to 7, and 7 goes right back to 6, and then nothing happens to the 8, so we can leave it alone. And then we'll combine the cycles into permutations. I'm sorry, not permutations, transpositions. And the trick for writing a transposition is for those 3 cycle, we always start with a 1, and then we feed in the other 2 numbers in reverse order. So we'll have a 1, 5 followed by 1, 4. Then same thing here. We'll have a 2, 3 followed by a 2, 9. And then this only has 2 elements, so it's just 6, 7. All right. So this is an odd permutation. It takes me 5 different transpositions to write out that product, and 5 is an odd number. Okay? All right. If we write the permutation as a product of disjoint cycles, so we've done this example several times now, where 1 goes to 4, 4 goes to 5, then 2, 9, 3, and then 6, 7, and then this 8 is kind of optional here. We call this vector here the cycle type. Okay? That is, this permutation, if I break it down, I get a cycle of length 3, another cycle of length 3, a cycle of length 2, and then a cycle of length 1. In a cycle type, order doesn't matter. If we wrote it as 3, 2, 3, 1, that would be fine also. But in practice, we usually write these in descending order. So this is the same, but we usually use descending order. All right. For a permutation in Sn, the numbers in the cycle type have to add up to n. Let me back up here. So this is 3, 3, 2, 1. This is 6, 7, 8, 9. Well, there are 9 elements in this set here that are being permuted. I am counting the fact that I have to list the ones. So the numbers in a vector indicating cycle type must add up to n. This means we include 1 cycles in the cycle type. Well, that makes a vector a partition of the integer n. So 3 plus 3 plus 2 plus 1 is just a partition of the number 9. There are more permutations than there are possible cycle types. So S26 has 26 factorial permutations, but it only has 2,436 cycle types. So that's a huge difference in magnitude. Permutations is on the order of 10 to 26, but if I just classify the cycle type, I'm down to 2.436 times 10 to the third. And so if we have to brute force, trying to identify the cycle type first will be more productive than trying to identify the permutation first. Okay? So that's one of the things to keep in mind. If we can narrow down the cycle type first, that will make the process of getting the permutation easier. All right. Let sigma and alpha be permutations in Sn. Then the conjugate of alpha by sigma by alpha is the permutation alpha sigma alpha inverse. So what we're doing is we're doing the inverse of a permutation first. Remember, we're what am I trying to say? We're working right to left. So we start with alpha inverse, then we do sigma, and then we do alpha. There is some background here, but the idea here is that if these were transformations, say, from one kind of vector space to another, we're converting from the standard basis vectors to some alternate bases. We're doing a permutation inside this alternate set, and then we are undoing what we did here and converting back from this alternate basis back into standard basis, for example. So what we're doing is alpha is doing some kind of conversion into another algebra or another vector space or another kind of system. We're doing the permutation sigma in that system, and then we convert everything back into the standard system. So that's what the alpha and the alpha inverse are doing, is we are looking at the effect that sigma has in an alternate system. All right, so let's try a couple of examples. Let's try conjugating 1, 3, 2 by 2, 3. So what that is we want alpha then sigma, and then alpha inverse. That should be alpha this time. So that will be 2, 3, followed by 1, 2, 3, followed by, it turns out 2, 3 again, because alpha only takes 2 elements and switches them, and so switching them back will be its inverse. All right, so let's see what happens. If we start with 1, this does nothing to a 1. This takes 1 and changes it to a 2, but then this takes a 2 and changes it to a 3. All right, so let's see what happens to 3 now. This pair changes a 3 to a 2. This takes a 2 and sends it back to a 3. This takes a 3 and sends it back to a 2. So what we end up with is 2 for that one. So let's see what happens to 2. This permutation changes a 2 to a 3. This changes a 3 back to a 1. And then this one doesn't do anything with a 1. So we're definitely closed in here. All right. Crap. I misread the problem. We were supposed to conjugate 1, 3, 2, and what I did was I conjugated 1, 2, 3. So let's try this again. 2, 3. We'll start with 1, 3, 2 this time, and then 2, 3. Well, let's see what happens. When we start with 1, this does nothing to a 1. This takes 1 to a 3, and then this takes a 3 to a 2. Then 2 goes to 3, 3 goes back to 2, and then 2 goes back to 3. They just ping-pong back a few times. 3 goes to 2, 2 goes back to 1, and then the last permutation doesn't do anything with 1. So as it turns out that 1, 2, 3 and 1, 3, 2 are just conjugates of each other. I just did the wrong one to begin with. So let's do a harder one. Let's do 1, 4, 5, 2, 3, and then 6. All right, so that's the one in the middle. By this permutation, alpha, which is 1, 6, 3, 4, 2, 5. And on the other side, I have to put alpha inverse. So alpha inverse. So how do we invert this? We write it backwards. 5, 2, 4, 3, 6, 1. And that means writing the individual permutations backwards, but it also means switching the order so that 1, 6, 3, which had been on the left, becomes 3, 6, 1, which is now on the right. So find the inverse of a permutation is pretty easy in this case. All right, so let's see what happens. Start with 1. 1 goes to 3. Doesn't do anything to 3. Doesn't do anything to 3. 3 goes to 2. Nothing happens to 2. 2 goes to 5, and then nothing happens to 5. Okay. Nothing happens to 5. 5 goes to 2. 2 goes to 3. Nothing happens to 3 until right here, and then 3 goes back to 1, and that closes off a cycle. So we've taken care of 1 and 5. So let's see what happens to this 4 that's in the middle here. This doesn't do anything to 4. 4 goes to 5. Nothing happens to 5. Nothing happens to 5. 5 goes to 1. Nothing happens to 1. 1 goes to 6. Okay, let's see what happens to 6. 6 goes to 1. Nothing happens to 1. Nothing happens to 1. Nothing happens to 1. 1 goes back to 4. But then 4 goes to 2. And then nothing happens to 2. Okay. Well, let's try one more. Let's see what happens to 2. Nothing happens to 2. 2 goes to 4. Nothing happens to 4. Nothing happens to 4. 4 goes to 5. But then 5 goes back to 4. And so we end up at 4. Okay? Well, by elimination, 3 should just go to itself. But let's double check. 3 goes to 6. Nothing happens to 6. 6 is nothing happens to 6 here either. 6 is just a 1 cycle. Okay. So 3 goes to 6, stays 6, stays 6, stays 6, stays 6, stays 6, and then at very end it goes to 3. So 3 eventually comes back out as 3. And so this is what we started with. This is the conjugate. But what I want to notice is that this has a 3 cycle and a 2 cycle and a 1 cycle. And this also has a 3 cycle and a 2 cycle and a 1 cycle. We won't have time to prove this theorem, but sigma and alpha of permutations, then any permutation and its conjugate have the same cycle type. That's kind of amazing if you think about in terms of what this conjugation is doing. We talked about the alpha as being a translation from their standard space, your standard geometry, to some alternate vector space or some alternate, some alternate field of working in. We turn the permutation in this alternate thing and see what happens there. What this is saying is that if sigma has a particular cycle type, say it is a 3 cycle, 1, 3, 2, it is a 3 cycle in the other alternate space also. It'll be 1, 2, 3 in that space. If we have a cycle type of 3 and then 2 and then 1, then we will have that same result after we've conjugated. It'll still be a 3 cycle and a 2 cycle and a 1 cycle after going through this convoluted series of stuff. So every permutation and its conjugates always have the same cycle type. And it turns out that the converse is true also. If I have 2 permutations that have the same cycle type, then I can build a permutation that makes one of them into the conjugate of the other. Okay? All right. We will pick up on Monday with what kind of cycle type do involutions have, and what kind of implications does that have for Enigma. And we will pick up from there. All right. Y'all take care.